Dear everyone, I am Dr. Fahim Mushtaq. Today we are going to discuss the advanced encryption standard. Before move to the history for the advanced encryption standard, I will tell you the objective for the today lecture, in which we discuss and review the brief history of AES and define the basic structure of AES. Also, we will discuss the transformation that used by the AES and the key expansion processes. Finally, we will discuss the different implementations in the AES. The NIST announced a call for the candidate of a cipher to the implementation of new encryption standard in 1997 because of the need of high security and efficiency. It's time to replace the existing DES and 3DS encryption algorithm with the new AES. All candidate of cipher submitted its proposal in 1998 and finalized in 2000. Finally, the Rijndael was selected as the AES out of 15 candidates. Rijndael is developed by Rijndael and John Diamond in 2001. The US government is employ AES to protect sensitive information and implemented across the world for data encryption purpose in the form of software and hardware. AES appear as the recent generation block cipher and significantly increases in the block size up to 128 bits, with the key size 128 bits, 192 bits and 256 bits. Here I want to remind you, in DES we have a block size only 128, right? The number of rounds set with the respective key size is 10, 12, 14 for 128 bit, 192 and 256 respectively. The number of AES parameters based on key length and parameters are the key size, block size, number of rounds. AES was designed with the following characteristics. The first important characteristic is that the compactness of code and speed on the large range of platform. Second characteristic is that the simple design, and finally third most important characteristic is the protection against the all known attack. The Rijndael proposal of AES define a cipher in which block length and the key length can be independently specified to be 128, 192 and 256 bit. The AES specification uses the same three key size alternatively but limits the block length to 128 bits. Rijndael is an academic submission based on the earliest squared cipher from Belgium academics Dr. Vincent Rijndael and Dr. John Diamond. It is a iterative cipher operate on entire data block in every round rather than a fistal operate on a half at a time, and was designed to have a characteristics of resistance against all non-attack, speed and code compactness on the wide range of platform, and design simplicity. The data unit of AES uses includes the 5 units of measurement to represent the data. The first is the bit, which is the smaller atomic unit, the binary digit with a value of 0, 1, we can say, which is the bit. Second is the byte, group of 8 bit treated as a single unit, a raw matrix 1 into 8 and column matrix 8 into 1. Here you can see the example for the byte. Here is the row matrix 1 into 8 and this one is the column matrix 8 into 1. The word a group of 4 byte 32 bits treated as a single entity, a raw matrix 1 into 4 and column matrix 4 into 1 of 4 byte, which is the word. Next is the data block or block group of 128 bit, a block can be represented as a raw matrix of 16 bytes. Here you can see the 16 byte, or we say 4 by 4 combination, which is also represent the 16 byte. This last, the data unit is the states. AES uses several rounds, each of which made of several stages. At the start and end of each round, AES uses the term data block. Before and after each stage, data block is referred as states. States are made of 16 bytes but normally treated as a matrix of 4 into 4 byte. How to make state matrix of data block of 16 byte? Now we will discuss the AES states. Each word, each 4 byte correspond to a column in state, which uses the simplified mathematics. All these states are representing a 4 into 4 matrix. We can say square matrix of 4 into 4, where we can say that B0 represent the coordinate S00, 0 row, 0 column. B1 represent the first row, 0 column. Okay, this depend upon the coordinates of the 4 by 4 matrices. Okay, here is second row and 0th column. I want to tell you, in first row we use the value as 0, second row we use the value as 1, third row we use the value of 2. Third row which say as 2 into 0, this is the coordinate for the B2. Similarly, fourth row and 0th column, the S into 3 into 0, which is B3. Similarly, all other value we will calculate it. Here you keep in mind the states. We will move from this way, then this way, up, then down, then again up. On this way you can have to write the each states is similar like that. Okay, here when you convert the state into matrix, again I want to repeat, you have to make the arrow from top to bottom, then bottom to top, then top to bottom, then bottom to top. Okay, okay, here is the block which represent B0 to B15 value. The block we represented I plus 4 into j, S into ij. States are moved into blocks. Again I repeat, B0 to B3, B4 to B7. This move arrow like that, B8 to B11, B12 to B15. We read and write the all this state in the form of state. The matrix we represented like that. Okay, here is the AES structure. This is the general structure for the AES algorithm. Here I again describe briefly the each states. AES is a non-fiscal cipher that encrypt and decrypt a data block of 128 bytes. It uses 10, 12, 14 round. The key size, which can be 128, 192, 256, depend on the number of rounds. This figure shows that the general design of encryption algorithm called cipher. The decryption algorithm called inverse cipher is similar, but the round key are applied in the reverse order. Only we have follow the same pattern of encryption, just have to reverse when we do the decryption process. Figure also show the relationship between the number of rounds and the key size, which mean that we have a three different AES version. They are referred as AES 128, AES 192, AES 256. However, the round key which are created by the key expansion algorithm are always 128 bits, the same size as the plain text or ciphertext block. Here we will discuss the round structure uh, of advanced encryption standard. The structure can be divided into four different stages. One is sub-byte, second is shift raw, mixed column, and round key. In first phase, each byte is transferred by S box. Uh, uh, the structure of each round at encryption side, each round except the last uses the force transmission that are invertible. The last round has only three transformation. And second is the shift raw, where the permutation is used to swap the bytes around. Third is the mix column, where we multiply the matrix to permit the bits within a byte. And finally, we add the round key, exclusive or reserved with the current round key. We will see the all operation in the next slides. This is the briefly description of all the four stages of each round. Now discuss each of four stages used in AES. The substitution byte stage uses a S box to perform a byte by byte substitution of block. There is a single 8-bit wide S box used on every byte. This S box is permutation of all 256 8-bit value constructed using a transformation which treated the value as polynomial Galvan field to power 8. However, it is fixed, so really only need to know the table when implementing. Decryption requires the inverse of the table. These tables are given in the next slide in the figure. We will see the table was designed to resistant to non-cryptanalysis attack. Specifically, the Rijndael sought a design that has a low correlation between input bits and the output bit, with the property that output cannot be described as a simple mathematical function of the input with no fixed point and no opposite fixed value. This diagram shows the byte substitution operate on each byte of state independently, with the input byte used in the index row or column in the table to retrieve the substitution value. Here you can see that the substitution value of byte xy in hexa format. Here this is the advanced encryption standard substitution box. Here this is the inverse substitution box of the advanced encryption standard. This is the example for the to convert the sub bytes into sub bytes, and after that inverse the sub bytes. In this transformation is used at the encryption side. To substitute a byte, we interpret the byte as two hexadecimal digits. The left digit defines the row and the right digit defines the column of substitution table. The two hexadecimal digits at the junction of the row and column are new byte. In the sub-byte transformation, state is created for matrix of byte. Transformation is done one byte at a time. The content of each byte is changed, but the arrangement of byte in the matrix remain the same. In the process, each byte is transferred independently. There are 16 distinct byte-to-byte transformation. The sub-byte operation involves 16 independent byte-to-byte transformation. The transformation definitely provide confusion effect. For example, 2 bytes 5 into A16 and 5 into B16, which differ only in 1 byte, the rightmost bit, and transfer to BE16 and 3916, which differ in 4 bits. Transformation using a Galvin field 2 power 8. AES also defines the transformation algebraically using GF 2 power 8 field with the irreversible polynomial. Polynomial as shown here is 1 x power 0, x power 1, here x power 3, x power 4 and x power 8. The inverse of each byte is computed in Galvin field using this polynomial. Resulting byte with the bit B0 to B7 is multiply of A into 8 a matrix X. With that, you have to find wherever the value not mentioned, like x square and x5 to 7, all these value are the 0. Okay. Resulting byte with the bit C0 to C7 added to 8 into 1 matrix Y to get the D. The sub-byte and inverse sub-byte transformation are inverse of each other. Finally, the multiplication or addition are done in Galvin field 2 with the mod 2 operation. Okay. Inverse of the substitution box, where we subtract the matrix D, multiply the inverse of matrix X and invert the Galvin field 2 power 8. We just have to inverse the previous process. Okay. Let us show the byte 0C transformation to FE by sub-byte routine and transform back to 0C by the inverse sub-byte routine. In sub-byte, the multiplication inverse of 0 into C in Galvin field 2 power 8 field is B0, which means B is here the value. Okay. Multiply the matrix X by the matrix result in C. The result of exclusive OR operation is D here, which is FE in hexadecimal. Similarly, we inverse the sub-byte operation. Here is the AES round structure. In the encryption, the transformation is called the shift row, and the shifting is to the left. The number of shift depend on the raw number 0, 1, 2, 3 and the state of the matrix. Here we can see that the example also. This means the raw 0 is not shifted at all and the last raw is shifted 3 byte. We note that when we do the inverse shift row operation in the decryption end, the transformation is called inverse shift row and the shifting is to the right. The number of shift is the same as the raw number 0, 1, 2, 3 and the state mix. I want to add that the algorithm for the shift row transformation is very simple. However, to emphasize that the transformation is one row at a time, we use a routine called shift row and the shift the bytes in single row. We call this routine 3 times. The shift routine first copy the row into temporary row matrix T. It then shifts the row. Here is the example to shift the row. You may have to see that in first case no change. Here one only coordinate change, two coordinate change. Here the three coordinates are changed. And how you have to fix this state into matrix, you can see here 63 fixed here, then F2, then C9, then FA, okay, which is the one column for this matrix, okay. Next stage is the mixed column stage. The substitution provided by the sub-byte transformation changes the value of byte based on the original value and entity in the table. The process does not include the neighboring byte. In mixed column transformation operate at column level. It transforms each column of a state to a new column. The transformation is actually the matrix multiplication of state column by constant square matrix. The bytes in the state column and constant matrix are interpreted as 8-bit word or polynomial with the coefficient in GF2. Multiplication of bytes is done GF2 power 8 with modulo. Here we can see the example. I repeat, the multiplication of byte is done GF2 power 8 with modulo operation. Or the polynomial 1 x, x3, x4 and x8. Here is the stages for the mixed column operation. The matrix multiplication make each bit dependent on every other bit in the word. Okay, you have to see there the multiplication. The mixed column stage is a substitution that make use of arithmetic over GF2 power 8. Each byte of a column is mapped into new value that is a function of all 4 bytes is the column. It is designed as a matrix multiplication where each byte is treated as polynomial of GF2 power 8. The inverse used for decryption involves a different set of constants. The constants used are based on linear code with maximal distance between code word. This gives a good mixing of the byte with each column. After that, we combine with the shift row step, provide good avalanches so that within a few rounds all output will depend on all the input bit. Here is the example for the mixed column and the inverse mixed column. Next stage is the add round key. This is last stage in which we proceed one column at a time. Also similar like the mixed column. Okay, it is similar to mixed column in this respect. Mixed column multiple a constant square matrix by each state column. Add round key added a round key word with each state column. The operation in the mixed column matrix multiplication. The operation in add round key is matrix addition. Since addition and subtraction in the field are same, the round key transformation are itself inverse. Now here the round key expansion. The key is broken into 4-byte words. AES uses, I want before move to the AES key expansion, generally I will tell you why AES use key expansion function, where if the number of round is n into r, the key expansion routine create nr plus 1 128-bit round key from one single 128-bit cipher key. The first round key is used for p-round transformation. The remaining round key are used for the last transformation at the end of each round. The key expansion routine creates round key word by word, where a word is an array of 4 bytes. The round create 4 into nr plus 1 word that are called the key expansion. Here we will see the key expansion, round key expansion of the root word and the subword. We will differentiate that. The root word, or we can say rotate word. Okay. Rotate word routine is similar to the shift word transformation, but it applied to only one row. The routine take a word as an array of 4 bytes and shift each byte to the left with wrapping. Second is the subword, which is also called the substitution word routine, is similar to the sub byte transformation, but it apply only to the 4 byte. The routine take each byte in a word and substitute another byte for it. Substitute another byte for it. Okay. Here is the key expansion of 128-bit. The process for the other two variants are same with the same slight change. You have to see the figure. All 44 words are made from the original key. The process are as follow. The first 4 words W0, W1, W2, W3 are made from cipher key. The cipher key is thought of as an array of 16 bytes K0 to K15. The first 4 bytes K0 to K3 become W0. The next 4 bytes K4 to K7 become W1, and so on. In other words, the concatenation of word in the group replicate the cipher key. The rest of the word Wi from I equal to 4 to 43 are made as follow. If I mod 4 not equal to 0, Wi equal to Wi minus 1 exclusive of Wi minus W4. Here is the example for the key expansion of the 128-bit cipher of advanced encryption standard. Just now we have discussed this process here, where we say that W0 to W3 are made for cipher key, and the I equal to 4 to 43 you can see in the left side in the key expansion are made for two different category. If I mod 4 not equal to 0, other is I mod 4 equal to 0. I mod 4 not equal to 0, which will the I W into I equal to W into I minus 1 exclusive of W into I minus 4, where I, if the I mod 4 equal to 0, where wi equal to t exclusive w into I minus 4. Here is the key expansion of discusses the three different key expansion. We will discuss previously 128. The processes of other two variant also the same, but only the slightly change. Key expansion algorithm in AES 192 and 256 variant are very similar to the key expansion algorithm 128. The following differences here explain the differences. 192 AES, where the word are generated in group of 6 instead of 4. In the AES 256, the word are generated in group of 8 instead of 4. The following steps are mentioned here. This is the design for the original advanced encryption standard, as we discussed earlier. At the end, I again explain the overview of detailed design of AES. First, the order of sub-byte and shift row is changed in reverse cipher. Second, the order of mix column and add wrong key is changed in the reverse cipher. The difference in ordering is needed to make each transformation in the cipher aligned with its inverse in the reverse cipher. Consequently, the decryption algorithm as a whole is the inverse of encryption algorithm. We have shown only 3 rounds, but the rest of the same. Note that the round key are used in reverse order. Note that encryption and decryption algorithm in original design are not similar. Thank you so much, guys, for the today lecture. Here we discuss the AES, and thank you for watching this video. If you have any query, question, then you have to comment on the YouTube channel. I will reply your comment wherever you find any issue. Thank you.